Tonight, we're going to confront a distance that will break your brain: Proxima Centauri. You've probably heard it called the nearest star to our sun. And when you hear the word nearest, your mind does something automatic. It assumes closeness. It assumes reachable. But here's what almost nobody truly grasps. The nearest star beyond our sun is so impossibly, outrageously far away that every familiar reference you have for distance collapses completely when you try to apply it. We're not talking about a long trip. We're not talking about a hard journey. We're talking about a gap so enormous that it makes the entire solar system, everything we've ever explored, look like a single grain of sand on an infinite beach. And by the end of tonight, you're going to understand exactly why. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand: distance. You deal with distance every single day of your life. You know how far it is from your bed to the kitchen. You know how long it takes to walk to the corner store. You know what it feels like to drive across town in traffic. Watching the minutes tick by as the buildings slowly change outside your window. These are distances your body understands, your legs understand them, your sense of time understands them. You don't need a calculator or a map to know roughly how far away something is in your daily life, because you've been practicing since you took your first steps as a child. A kilometer is about the distance you can walk in 10 to 12 minutes at a comfortable pace. It's a manageable chunk of the world. You can see a kilometer ahead of you on a straight road. You can picture it in your mind. You've walked that distance thousands of times, maybe tens of thousands of times over the course of your life. It's a human distance. It belongs to us. It fits into our experience the way a shoe fits a foot. Naturally, comfortably, without any strain. This sense of distance is hardwired into us. It's part of what makes us human. If someone tells you a shop is 3 kilometers away, you instantly know what that means. It's a 30-minute walk, a 5-minute drive, maybe a 15-minute bike ride. You don't have to think hard about it. Your brain processes it effortlessly because it maps onto experiences you've already had. And if someone says a city is 300 kilometers away, you can handle that too. It's about 3 hours of driving. You'll want some music or a podcast, maybe a stop for coffee halfway. You can plan around it. You can picture the journey because it's still within the realm of human experience. People drive 300 kilometers all the time. It's routine. It's ordinary. It's nothing special. Even the longest distances on Earth, while impressive, are still manageable for the human mind. The distance from New York to Los Angeles is about 3,900 kilometers. That's a long way. It takes about 5.5 hours by plane. You cross the entire North American continent, watching the landscape shift from the dense urban sprawl of the East Coast to the flat expanse of the Great Plains, to the dramatic ridges of the Rocky Mountains, and finally to the Pacific coastline. It's a serious distance, but people make that journey every day. Thousands of flights cross the continent daily. The distance is large, but it's within our grasp. We can picture it. We can relate to it. We've either made a similar journey ourselves, or we know someone who has. It doesn't frighten us or overwhelm us. It's just a long trip. The circumference of the Earth at the equator is about 40,075 kilometers. That's bigger than most people ever travel in a single journey, but it's still a number we can work with. Humans have been circumnavigating the globe for over 500 years. Ferdinand Magellan's expedition set out in 1519, and the surviving crew completed the journey in 1522, taking about 3 years to sail around the world. Today, a commercial aircraft could circle the Earth in roughly 45 hours of continuous flight time. The Earth is big from our perspective, standing on its surface. Oceans stretch to the horizon. Continents take days to cross. Mountains seem to touch the sky. But the Earth is a finite, measurable thing. We've mapped every square kilometer of it. We've walked on its highest peaks and dived to its deepest ocean trenches. We know its shape, its size, its weight. It's our home, and we understand it. We have conquered its distances with ships and trains and planes and automobiles. No point on Earth is more than about a day of air travel from any other point. The planet that once seemed infinite to our ancestors is now a place we can cross before our next meal. But now, let's take one step off our planet. Just one step. And watch what happens to our comfortable sense of distance. Watch how quickly everything we thought we understood about far and near falls apart. The moon orbits Earth at an average distance of about 384,400 kilometers. Already, something has changed. 384,400 kilometers. That number is harder to feel. It doesn't connect to anything in your daily experience the way 3 kilometers to the shop does. There's no road to the moon. There are no landmarks along the way. There's no scenery to watch, just a void. A gap of pure empty space between here and there. You can't walk to the moon. You can't drive. You can't sail. You can't even fly in any conventional sense. You need a rocket. You need enormous amounts of energy just to escape Earth's gravity. And then you need 3 days of coasting through nothing to get there. Think about what the Apollo astronauts experienced. They climbed into a capsule mounted on top of the Saturn V rocket, the most powerful machine ever built at that time. The rocket stood about 111 meters tall, taller than the Statue of Liberty. It burned through enormous quantities of fuel in just minutes to hurl the astronauts fast enough to escape Earth's gravitational pull. They needed to reach a speed of about 11 kilometers per second. That's roughly 39,600 kilometers per hour, about 400 times faster than typical highway driving. If you were driving on a highway at 100 kilometers per hour and an object passed you at 11 kilometers per second, it would be gone before your brain could register that anything had happened. It would be a blur, a flash, something so fast that your nervous system couldn't keep up. And even at that extraordinary speed, it still took 3 days to reach the moon. 3 full days of traveling through the vacuum of space, covering 384,400 kilometers of emptiness. No gas stations, no rest stops, no scenery, just the slowly shrinking Earth behind them and the slowly growing moon ahead of them. The astronauts spent 3 days inside a capsule roughly the size of a large car, hurtling through nothingness at speeds no human had experienced before, just to reach the nearest celestial object to Earth. For most of that journey, there was nothing to see outside the windows except the blackness of space and the unchanging stars. The Earth grew smaller behind them, eventually becoming something they could cover with their thumb held at arm's length. The moon grew larger ahead of them, changing from a bright disk in the sky to a real, cratered, 3-dimensional world. But between those 2 points, there was nothing. Just distance. Pure, featureless, silent distance, stretching in every direction. Here's another way to think about the Earth-Moon distance. If you could somehow line up Earth side by side, you would need to place about 30 of them in a row to fill the gap between Earth and the Moon. 30 Earths. Each one nearly 13,000 kilometers across. Lined up one after another through empty space. That's how far the Moon is. And the Moon is close. It's our nearest neighbor. It's so close that you can see it with your naked eye on most clear nights. You can see craters on its surface with a pair of ordinary binoculars. It's right there, hanging in the sky, seemingly within reach. And yet it takes 3 days of rocket travel at speeds that would be lethal if you hit anything along the way. When the Apollo astronauts spoke to Mission Control from the moon, their words traveled at the speed of light, 300,000 kilometers per second, the fastest speed anything can travel in the universe. And even at that speed, there was a delay, about 1.3 seconds each way. The astronaut would say something, and 1.3 seconds later, Mission Control on Earth would hear it. When Mission Control responded, their words took another 1.3 seconds to reach the moon. It created a round-trip delay of about 2.6 seconds. Subtle, but real. You can hear it in the recordings. there's always this slight pause, this tiny lag, a reminder that even though the moon looks close, even though you can see it without any equipment at all, it's far enough away that light itself needs over a second to make the trip. And here's the thing, the moon is by far the closest celestial body to Earth. It's our nearest cosmic companion, the only other world humans have ever set foot on. Everything else in space is much, much farther away. Everything. Now let's take another step outward. Let's talk about the sun. The sun is approximately 150 million kilometers from Earth. Astronomers call this distance 1 astronomical unit, or AU, and they use it as a baseline for measuring other distances within the solar system. 150 million kilometers. Say it slowly. 150 million. That's a number that starts to lose its grip on meaning. You can write it down, you can do math with it, but you can't feel it. There's nothing in your daily life, nothing in the entire range of human experience that prepares you to understand what 150 million kilometers actually means. It's about 390 times farther than the moon. Remember the moon? The thing that took 3 days of rocket travel to reach? Multiply that distance by 390 and you get to the sun. The moon, which already seemed impossibly far away, is barely a fraction of the way to our own star. Let's try to make it more concrete. If you could drive to the sun at highway speed, say 100 kilometers per hour, non-stop, no breaks, no sleeping, no refueling, just constant driving through space at highway speed, it would take you about 171 years. Not days, not months, years. More than 2 full human lifetimes of continuous driving. Your great-grandchildren would still be driving. Their children might finally arrive. You would have been dead for over a century before the car you started in reached its destination. Generations of your family would be born and would die inside that car, each one inheriting the wheel from the last, each one driving toward a destination that none of them chose, but all of them are bound to. Now, remember those Apollo astronauts traveling at 11 kilometers per second? At that speed, which required one of the most powerful rockets ever built, reaching the sun's distance would take about 158 days. That's more than 5 months of non-stop travel at a speed that would cross the entire United States in roughly 6 minutes. 5 months at a speed so fast that your brain can barely comprehend it, and you'd only just reach the distance of the sun. Light covers this distance in about 8 minutes and 20 seconds. When you look at the sun, assuming you're doing so safely, you're not seeing it as it is right now. You're seeing it as it was 8 minutes and 20 seconds ago. The photons entering your eye at this moment left the sun's surface over 8 minutes before you saw them. If the sun suddenly vanished right now, you wouldn't know for over 8 minutes. You'd keep seeing it, keep feeling its warmth, completely unaware that the source was already gone. For 8 minutes and 20 seconds, you'd be living in a world that no longer existed, bathed in the light of a star that had already disappeared. This has a practical consequence that most people never think about. When we operate spacecraft near other planets, we can't control them in real time because light takes too long to travel the distance. Mars, at its closest approach to Earth, is about 55 million kilometers away. That's roughly 3 light minutes. At its farthest, when Earth and Mars are on opposite sides of the Sun, the distance stretches to about 400 million kilometers, over 22 light minutes. When NASA engineers send a command to a rover on Mars, that command travels at the speed of light, the fastest anything can move in the universe, and it still takes between 3 and 22 minutes to arrive, depending on where Mars is in its orbit. If the rover encounters a problem, an unexpected rock in its path, a steep slope, a software glitch, mission control won't know about it for minutes, and their response won't arrive for additional minutes after that. A simple problem that you could solve in seconds with a remote control car on Earth might take an hour or more to resolve on Mars. Not because the engineers are slow, but because the universe imposes a speed limit on information itself. Nothing moves faster than light. No signal, no radio wave, no message of any kind can exceed 300,000 kilometers per second. And even that ultimate speed isn't fast enough to make communication across our solar system feel instant. The universe is simply too big. Now, let's pause here and think about what we've established so far. We started with distances you understand intuitively. A kilometer, a city, a continent, the circumference of the Earth. These are distances that fit comfortably into human experience. Then we stepped off the planet and went to the moon, 384,400 kilometers away, already far beyond anything we experience in daily life, requiring 3 days of rocket travel at extraordinary speeds. Then we reached the Sun, 150 million kilometers away. A distance so vast that driving there would take nearly 2 centuries, and even light needs over 8 minutes to cross it. Each step has taken us dramatically farther than the last. The moon is about 30 times the diameter of the Earth away from us. The Sun is about 390 times farther than the moon. We've gone from human-scale distances to planetary-scale distances to the scale of the inner solar system. And at each step, the numbers have grown so large that they've started to slip out of our intuitive grasp. 150 million kilometers doesn't mean anything to your gut. It's just a big number. Your brain sees it as large, files it in the same mental category as other large numbers, and moves on. You can't picture it. You can't feel it. You can't relate it to anything you've ever experienced. If you took every road on Earth, every highway, every country lane, every dirt path in every village on every continent, and laid them all end to end, you cover only about 64 million kilometers, less than half the distance to the Sun. You'd need to lay them all out twice over just to get close. All the roads humanity has ever built, doubled, still wouldn't bridge the gap to our own star. But here's what I need you to understand. Everything we've talked about so far, every distance, every comparison, every mind-bending number, all of it is essentially nothing compared to what's coming. The distance from the Earth to the Moon, cosmically insignificant. The distance from the Earth to the Sun, a tiny step. The entire inner solar system with all its planets, its asteroid belt, its hundreds of millions of kilometers of empty space, it barely registers on the scale we're building toward. Because we haven't even left our own solar system yet. And the star we're trying to reach, Proxima Centauri, the nearest star beyond the Sun, the closest stellar neighbor we have, is not inside our solar system. It's outside, way outside. So far outside that the word outside doesn't begin to capture the reality. The distance from the Sun to Proxima Centauri is so much greater than the distance from the Earth to the Sun that the comparison almost seems unfair. It's like comparing the thickness of a sheet of paper to the distance across an ocean. They're both distances, technically, but they exist on completely different scales. Scales so different that your brain wants to treat them as separate categories of reality. But I'm getting ahead of myself. Before we can truly appreciate how far away Proxima Centauri is, we need to understand the full scale of our own solar system. We need to see how big our cosmic home really is, how far the Sun's influence extends, how much empty space exists between the planets. Because only when you've grasped the full, staggering enormity of the solar system will you be prepared for the revelation that the distance to the nearest star makes all of it look like nothing. Let me set the stage with one more comparison to make sure the Earth-Sun distance is truly anchored in your mind. The Earth-Sun distance of 150 million kilometers is often used as a yardstick in astronomy. It's called 1 astronomical unit precisely because it's a convenient reference distance within our solar system. Mars orbits at about 1.5 astronomical units from the Sun, roughly 228 million kilometers. Jupiter is about 5.2 astronomical units out, approximately 778 million kilometers from the Sun. Saturn is at about 9.5 astronomical units. These numbers are already enormous. Jupiter is more than 5 times farther from the Sun than Earth is. Saturn is nearly 10 times farther. But they're still within the realm of things we can at least put numbers to, even if those numbers don't have any intuitive meaning. The speed of light gives us another useful way to think about these distances. Light from the Sun takes about 8 minutes and 20 seconds to reach Earth. To reach Mars, it takes about 12 to 14 minutes, depending on where Mars is in its orbit. To reach Jupiter, light needs about 43 minutes. To reach Saturn, about 79 minutes. More than an hour for light, the fastest thing in the universe, to travel from the Sun to Saturn. Think about that. Light can circle the entire Earth 7.5 times in a single second. It moves at a speed that makes everything else in human experience seem frozen in place. And yet, it needs over an hour just to get from the Sun to Saturn. That tells you something profound about how big even our local neighborhood of space really is. And Saturn isn't even close to the outer boundary of our solar system. There are worlds much farther out. There are regions of our solar system so distant that the Sun itself fades to just another bright star in the sky. Regions so remote that sunlight, even traveling at 300,000 kilometers per second, takes hours to reach them. We're going to explore those regions next. We're going to travel outward past the gas giants, past the ice giants, past the Kuiper Belt, to the very edge of the Sun's influence. And when we get there, when we've seen just how impossibly vast our own solar system really is, we're going to discover something that might change how you think about the universe forever. The nearest star isn't just far away, it's far away in a way that redefines the word far. It's far away in a way that takes the entire solar system, everything we've ever explored, every planet we've ever photographed, every space probe we've ever launched, and reduces all of it to a single point. A dot. A speck so small, it vanishes against the backdrop of the interstellar void. That's where we're headed. And trust me, you're not ready for it. Nobody ever is. Because the human mind was never built to comprehend distances like these, our brains are extraordinary at judging the distances that matter in everyday life. You can close your eyes right now and estimate the distance to the nearest door within a few % accuracy. You can throw a ball to someone across a field, and your brain automatically calculates the trajectory, the force, the timing, all without conscious thought. We are beautifully calibrated for the world we can see and walk through. But that calibration has limits, hard limits. When distances grow beyond the horizon, beyond the edge of what any human could walk in a lifetime, our intuition simply shuts down. It has nothing to grab onto, no reference points, no experience to draw from. The numbers become abstract, weightless, meaningless to the gut, even as the mind writes them down and does the math. When you hear a number like 40 trillion, your mind doesn't process it as a distance. It processes it as a sound, as a word, as an abstract concept that sits in the same mental bin as other large numbers you've encountered. 10,000, a million, a billion, a trillion. They all feel vaguely similar to your intuitive brain. They're all just big. But the differences between them are staggering, and the distances they represent when we're talking about space are so different from each other that they might as well be measured in different units. We can calculate it. We can write equations that describe it. We can build instruments that measure it. But we can't feel it the way we feel the distance to the next town. That gap between calculation and intuition, between knowing a number and understanding what it means, is at the heart of everything we're about to explore. The distance to Proxima Centauri isn't just large, it's large in a way that exposes the limits of human cognition. It's large in a way that forces us to confront how small we really are and how vast the universe really is. But that confrontation is valuable. Understanding the true scale of the distance to the nearest star is one of the most important things you can do for your cosmic perspective. Because once you truly grasp it, once you really understand what 4.24 light years means, you stop taking the universe for granted. You stop assuming that the stars are within reach. You stop thinking of space as just a bigger version of the sky above your backyard, and you start to see the cosmos for what it really is. An ocean of emptiness so vast that even the nearest shore is almost impossibly far away. The stars that look so close on a clear night, pinpricks of light that seem to hang just above the treetops, are separated from us by distances that would take our fastest machines thousands of years to cross. What looks like a familiar ceiling of light is actually a window into an emptiness so vast that crossing even the smallest gap in it would take longer than civilizations last. So, let's keep going. Let's leave Earth and the inner solar system behind and push outward into the deeper reaches of our cosmic neighborhood. Let's see how big the solar system really is, and why even its full, breathtaking scale is nothing more than a warm-up for the distance we're ultimately trying to understand. Now let's push outward. We've covered the distance from Earth to the Moon, and from Earth to the Sun. We've seen how even these relatively close cosmic neighbors are separated by distances that dwarf anything in our daily lives. But we've barely scratched the surface of our own solar system. Because the solar system doesn't end at Earth's orbit. It doesn't end at Mars. It doesn't end at Jupiter or Saturn. It extends outward for billions and billions of kilometers, reaching into regions so remote that the sun itself shrinks to a faint point of light, barely distinguishable from the background stars. And to truly appreciate how far away Proxima Centauri is, you first need to understand just how enormous the space we already call home really is. Let's start with the gas giants. Jupiter, the largest planet in our solar system, orbits at an average distance of about 778 million kilometers from the Sun. That's roughly 5.2 times the Earth-Sun distance. To put that in terms we've already established, remember that light from the Sun takes about 8 minutes and 20 seconds to reach Earth. That same light needs about 43 minutes to reach Jupiter. 43 minutes at 300,000 kilometers per second. If you tried to drive to Jupiter at highway speed, it would take you roughly 890 years. Not to Jupiter and back, just to Jupiter. One way. You would need to drive continuously for nearly 9 centuries just to arrive. Jupiter itself is a monster of a planet. It has a diameter of about 139,820 kilometers. That's roughly 11 times wider than Earth. You could line up more than 11 Earths across Jupiter's face and still have room to spare. Its volume is so enormous that about 1,321 Earths could fit inside it. Jupiter contains more mass than all the other planets in the solar system combined. This single planet dominates the outer solar system through its gravity, pulling on asteroids and comets, shaping the orbits of other worlds, and acting as a kind of cosmic shield that deflects some incoming debris away from the inner planets. Some scientists believe Jupiter's presence may have been essential for life on Earth by reducing the number of catastrophic impacts our planet experienced over the past 4 billion years. Jupiter has storms larger than our entire world. The Great Red Spot, Jupiter's most famous feature, is a storm system that has been raging for at least 400 years. At its widest, it was about 3 times the diameter of Earth. Even today, after centuries of slow shrinking, it remains larger than our planet. Think about that. A single storm on Jupiter, one weather pattern on one planet, is bigger than the entire world you live on. Everything you've ever known, every city, every mountain range, every ocean, all of it would fit inside a storm on Jupiter, with room to spare. Jupiter also has at least 95 known moons, including 4 large ones discovered by Galileo in 1610. One of those moons, Europa, has a smooth, icy surface beneath which almost certainly lies a global ocean of liquid water containing perhaps twice as much water as all of Earth's oceans combined. Another moon, Ganymede, is larger than the planet Mercury. Jupiter isn't just a planet. It's practically a miniature solar system unto itself. But Jupiter, enormous as it is is still relatively close to the Sun in the grand scheme of the solar system. Saturn orbits much farther out, at an average distance of about 1,434,000,000 kilometers from the Sun. That's roughly 9.5 astronomical units. Light from the Sun takes about 79 minutes to reach Saturn, more than an hour. When the Cassini spacecraft orbited Saturn from 2004 through 2017, every command sent from Earth took over an hour to arrive. Every image Cassini captured took over an hour to travel back. Mission controllers couldn't react to what the spacecraft was seeing in real time. They had to program entire sequences of commands days or weeks in advance, upload them, and trust that the spacecraft would execute them correctly billions of kilometers away. If something went wrong, the spacecraft had to handle it on its own, because by the time Mission Control received the distress signal, figured out a solution, and transmitted new commands, well over 2 hours would have passed. Saturn's ring system is one of the most spectacular sights in the solar system. The rings extend from about 6,600 kilometers above Saturn's cloud tops to roughly 80,000 kilometers outward. They're made of countless particles of ice and rock, ranging from tiny grains to chunks the size of houses, all orbiting Saturn in a vast flat disk. And yet, despite extending for tens of thousands of kilometers, the rings are remarkably thin. In most places, they're only about 10 meters thick. If you scaled Saturn down to the size of a basketball, its rings would be thinner than a razor blade. Beyond Saturn, we enter the realm of the ice giants. Uranus orbits at about 2,871,000,000 kilometers from the Sun. That's roughly 19.2 astronomical units. Light from the Sun takes about 2 hours and 40 minutes to reach Uranus. 2 hours and 40 minutes at the fastest speed the universe allows. Uranus is tilted almost completely on its side, with an axial tilt of about 98 degrees. No one knows exactly why. The most likely explanation is that early in the solar system's history, something enormous slammed into Uranus and knocked it over. Whatever hit it must have been massive, perhaps the size of Earth itself, to tilt an entire planet sideways. This extreme tilt means that for part of its orbit, one of Uranus's poles points almost directly at the Sun, experiencing continuous sunlight for about 42 Earth years, while the opposite pole sits in total darkness for the same duration. Neptune is the farthest known planet from the Sun, orbiting at an average distance of about 4,495,000,000 kilometers. That's roughly 30 astronomical units, 30 times the distance from Earth to the Sun. Light from the Sun needs about 4 hours and 10 minutes to reach Neptune. 4 hours. In the time it takes sunlight to travel from the Sun to Neptune, you could watch 2 full movies, cook an elaborate dinner, or drive from one end of a small country to the other. And during all that time, that light would be traveling at 300,000 kilometers per second, without stopping. Neptune takes about 165 Earth years to complete a single orbit around the Sun. It was discovered in 1846, which means it only just completed its first full orbit since discovery around 2011. In all the centuries since we first spotted it, Neptune has barely finished one single lap around the Sun. That is how slowly time passes in the outer solar system. Neptune is a world of extremes. Wind speeds on Neptune reach up to 2,100 kilometers per hour. Those are the fastest sustained winds measured on any planet in the solar system. To put that in perspective, the strongest hurricanes on Earth have wind speeds of about 300 kilometers per hour. Neptune's winds are roughly 7 times faster than the most destructive storms our planet has ever produced. These ferocious winds howl across a world so distant that the Sun, from Neptune's cloud tops, would appear as little more than a very bright star. You could block it out with a pinhead held at arm's length. The overwhelming, life-giving Sun that dominates Earth's sky would be reduced to a tiny point of light from Neptune. Still by far the brightest object in Neptune's sky, still dazzling, still unmistakable, but no longer the blazing disk we know. Just a point. A brilliant, sharp point of light that you could blot out with the head of a pin. Still vastly brighter than any star, but no longer the warm, commanding presence that fills our skies on Earth. When the Voyager 2 spacecraft flew past Neptune in 1989, it was one of humanity's greatest achievements in exploration. That spacecraft had been traveling for 12 years since its launch in 1977, using gravitational assist from Jupiter and Saturn to build up enough speed to reach the outer solar system. When Voyager 2 arrived at Neptune, it was approximately 4.4 billion kilometers from Earth. The radio signals it sent back, traveling at the speed of light, took over 4 hours to reach us. Every photograph, every measurement, every piece of data was over 4 hours old by the time scientists on Earth saw it. They were looking at Neptune's past, not its present, separated by a communication delay imposed by the vast distance between them. But here's the thing that most people don't realize. Neptune's orbit doesn't mark the edge of the solar system, not even close. Beyond Neptune lies a vast region that extends far, far beyond the last planet. And this is where distances in our solar system truly become staggering. The Kuiper Belt begins just beyond Neptune's orbit and extends outward to roughly 50 astronomical units from the Sun. That's about 7,500,000,000 kilometers. This region is filled with icy bodies left over from the formation of the solar system 4.5 billion years ago. These are frozen relics, ancient chunks of ice and rock that never came together to form a planet because the material out here was too spread out and the gravitational forces too weak to pull it all together. There are thousands of known objects in the Kuiper Belt, and astronomers believe there may be hundreds of thousands more waiting to be discovered. Some of these objects are substantial. Eris, discovered in 2005, is slightly more massive than Pluto. Makemake and Haumea are also large enough to be classified as dwarf planets. These are not tiny pebbles drifting in the dark. They're worlds in their own right, some with moons of their own, each one a frozen time capsule from the earliest days of the solar system. Pluto, which was considered the 9th planet from its discovery in 1930 until 2006, lives in the Kuiper Belt. Pluto's orbit takes it between about 4.4 billion and 7.4 billion kilometers from the Sun. At its most distant point, light from the Sun takes nearly 7 hours to reach Pluto. 7 hours for light to make the trip. If you sent a message to a spacecraft near Pluto, traveling at the speed of light, you would have to wait nearly 7 hours for that message to arrive, and another 7 hours for any response to come back. That's a 14-hour round trip for information, traveling at the ultimate speed limit of the universe. When NASA's New Horizons spacecraft flew past Pluto in July of 2015, it sent back the first detailed images of this distant world. Those images revealed a complex, geologically active surface with mountains of water ice, vast plains of frozen nitrogen, and a thin atmosphere extending much farther than anyone expected. Pluto had a heart-shaped region on its surface, informally named the Heart, that captured the world's imagination. But receiving those images was an exercise in patience. Each photograph took over 4 hours to travel from New Horizons to Earth. And because the spacecraft's transmitter was relatively weak, and the distance was so enormous, the full dataset from the flyby took over 15 months to transmit back to Earth. 15 months to send home the data from a flyby that lasted only a few hours. That's how far away the Kuiper Belt is. But the Kuiper Belt, vast as it is still not the boundary of the solar system. Beyond it lies something even more remote. Something so distant that it redefines what we mean when we say, our solar system. The Oort Cloud. The Oort Cloud is a theoretical shell of icy objects that surrounds our entire solar system, like a vast, sparse, spherical bubble. No one has ever directly observed an Oort Cloud object. We've never photographed one. We've never sent a spacecraft anywhere near one. No telescope has ever captured an image of a body sitting in the Oort Cloud. It's too far away and the objects are too small and too faint. We know the Oort Cloud exists because of comets. Long-period comets, the ones that take hundreds or thousands or even millions of years to complete a single orbit around the Sun, must originate from a distant reservoir of icy bodies. The orbits of these comets, traced backward using precise mathematical calculations, point to a source region far beyond the Kuiper Belt. That source region is the Oort Cloud. It's the solar system's deep freezer, a vast cold storage of primordial ice sitting at the very edge of the sun's gravitational reach, where our star's gravity is so weak that a passing star's influence can dislodge objects and send them tumbling inward on orbits that take millions of years to complete. The inner edge of the Oort cloud is estimated to begin at roughly 2,000 astronomical units from the Sun. That's 2,000 times the distance from Earth to the Sun, about 300 billion kilometers. Already, this is a distance so large that it's hard to make meaningful comparisons, but the outer edge of the Oort cloud extends even farther. Estimates place it at roughly 100,000 astronomical units from the Sun, 100,000 times the Earth-Sun distance. That's about 15 trillion kilometers. And here's the number that should stop you in your tracks. The outer edge of the Oort cloud is roughly 1.5 to 2 light years from the Sun. Let that sink in. The solar system, our solar system, the region of space gravitationally bound to our star, extends roughly 2 light years in every direction. When someone asks how big the solar system is, most people think of Neptune's orbit, about 60 astronomical units across, roughly 9 billion kilometers in diameter. That's the planetary solar system, the part with the familiar 8 planets. But the true solar system, including the Oort cloud, is thousands of times larger than that. If the planetary solar system from the Sun to Neptune were the size of a coin sitting in the center of a room, the Oort cloud would extend to the walls of a building several city blocks away. This is where Voyager 1 becomes our most powerful tool for understanding scale. Voyager 1 launched on September 5th, 1977. It's been traveling through space for nearly 50 years. It carries a golden record containing sounds and images from Earth, a message in a bottle thrown into the cosmic ocean just in case someone out there might find it. The record includes greetings in 55 languages, music ranging from Bach to Chuck Berry, natural sounds like thunder and birdsong, and 115 images showing life on Earth. It was assembled by a committee chaired by the astronomer Carl Sagan, who saw it as a way of saying, "We were here, we existed, we reached for the stars." That record is now the most distant human artifact in existence, drifting through the interstellar void, carrying with it a portrait of a civilization that may or may not still exist by the time anything finds it. Voyager 1 has been moving at about 17 kilometers per second ever since it received its last gravitational assist from Saturn in 1980. 17 kilometers per second. That's roughly 61,200 kilometers per hour. At that speed, you could cross the entire United States from coast to coast in under 4 minutes. You could circle the Earth in roughly 40 minutes. It's a speed that would be lethal, incomprehensible, terrifying if you could somehow experience it. And Voyager 1 has been traveling at that speed without stopping for nearly half a century. No fuel is needed to maintain this speed in the vacuum of space. There's nothing to slow it down. No air resistance, no friction, no obstacles. Just the endless frictionless void of space, and Voyager 1 sailing through it at 17 kilometers every second, day after day, year after year, decade after decade. As of 2025, Voyager 1 is approximately 24 billion kilometers from Earth. That's about 163 astronomical units. It crossed the heliopause in 2012, the boundary where the solar wind finally weakens and gives way to the interstellar medium, the thin gas and particles that drift between the stars. When Voyager 1 crossed that boundary, it became the first human-made object to enter interstellar space. It was a historic moment, celebrated around the world. Humanity had finally reached beyond its own star's influence and touched the space between the stars. But let's put Voyager 1's position in perspective. After nearly 50 years of travel at 17 kilometers per second, Voyager 1 has covered about 163 astronomical units. The inner edge of the Oort Cloud is at roughly 2,000 astronomical units. Voyager 1 hasn't even reached the beginning of the Oort Cloud yet. It would need to travel for roughly another 500 years before it reached the inner edge. 500 more years of coasting through empty space at 61,000 kilometers per hour before it even touches the outermost fringe of the Oort Cloud. And the outer edge, at 100,000 astronomical units, at its current speed, Voyager 1 would need about 30,000 years to reach the outer boundary of our solar system. 30,000 years. That's roughly as long as the time since the last ice age. That's longer than all of recorded human history, multiplied several times over. If Voyager 1 had launched when the first cave paintings were being made at Lascaux in France, roughly 17,000 years ago, it still wouldn't have reached the outer edge of the Oort Cloud today. It would still be traveling, still coasting through the darkness, still nowhere near the true boundary of the solar system. Entire civilizations that we know nothing about could have risen and fallen in the time Voyager 1 needs to exit our solar system. This means that our fastest, most distant spacecraft, the object that humanity has flung the farthest into space, has traveled less than 1 light day from the Sun, after nearly 50 years, less than 1 light day. And the solar system extends to roughly 2 light years. Voyager 1 has crossed less than 1/700th of the solar system's full extent. It's traveled an incredible distance by human standards, farther than any object we've ever built. But compared to the true size of the solar system, it's barely moved. It's like stepping out your front door and declaring that you've explored the continent. You've taken 1 step out of millions. Think about what this means for any attempt to leave the solar system entirely. If it takes Voyager 1 30,000 years just to reach the outer edge of the Oort Cloud at 17 kilometers per second, then crossing the solar system with current technology isn't just difficult. It's a project that spans geological timescales. Civilizations rise and fall in less time than it would take Voyager 1 to leave our solar system behind. Languages evolve beyond recognition. Species go extinct and new ones emerge. Continents shift measurably on Earth's surface. And Voyager 1 would still be traveling, still inching its way through the Oort Cloud, surrounded by ancient cometary bodies drifting in the cold darkness at the farthest reaches of the Sun's gravitational grasp. Let me offer you one more comparison to drive this home. If you built a scale model of the solar system where the Sun was the size of a basketball, about 24 centimeters across, then Earth would be a tiny grain roughly the size of a peppercorn, about 2.1 millimeters across, sitting about 26 meters away. That's already a significant distance in a model. The Sun is the size of a basketball, Earth is a peppercorn 26 meters away. You'd need a large room just to contain the inner solar system at this scale. Jupiter would be about the size of a large marble, sitting roughly 135 meters from the basketball Sun. Saturn would be a slightly smaller marble at about 247 meters. Neptune would be a small bead roughly 775 meters away, more than half a kilometer from the basketball Sun. But the Oort Cloud, the true edge of the solar system at this scale, the outer boundary of the Oort Cloud would be roughly 2,600 kilometers from the basketball Sun. 2,600 kilometers. In a model where the Sun is the size of a basketball, you would need to travel farther than the distance from London to Moscow just to reach the outer edge of the Oort Cloud. The entire planetary solar system from the Sun to Neptune, the part with all 8 planets, every world we've ever studied and sent spacecraft to, all of it would fit within about 775 meters. A brisk 10-minute walk. But the Oort Cloud would extend for thousands of kilometers beyond that. The model wouldn't fit in any single country. It would span an entire continent. That's how much bigger the full solar system is compared to the familiar part we usually think of. And here's the fact that should truly unsettle you. The fact that this entire section has been building toward. In this same scale model, where the Sun is a basketball and the planets are peppercorns and marbles, spread across a few hundred meters, where the Oort Cloud stretches for thousands of kilometers in every direction, Proxima Centauri would be another ball sitting roughly 6,500 kilometers away. 6,500 kilometers from the basketball sun. In a model where the entire planetary solar system fits within a 10-minute walk, the nearest star would be farther than the distance from New York to Tokyo. You would have to cross the Pacific Ocean to reach the nearest star in this model. The gap between the outer edge of the Oort Cloud and Proxima Centauri is still vastly larger than the solar system itself. Even after you've traveled through the entire Oort Cloud, after you've crossed the full unimaginable breadth of our solar system, you've only covered a small fraction of the distance to the nearest star. The solar system is enormous. It stretches for trillions of kilometers. It contains 8 planets, hundreds of moons, millions of asteroids, billions of comets, and a vast shell of icy bodies extending nearly 2 light years from the sun. It is so large that our fastest spacecraft would need 30,000 years to cross it. It is so large that light itself needs hours to traverse the space between its planets and years to reach its outermost boundaries. It is so large that the human mind genuinely struggles to comprehend it, even with analogies and scale models and comparisons to familiar things. The solar system is the biggest thing most people can imagine when they think about space, the largest structure they consider to be home. And yet, it's tiny. Compared to the distance to Proxima Centauri, the entire solar system is tiny. The distance to the nearest star makes the full extent of the solar system look like a puddle next to an ocean. Everything we've ever explored, every planet we've ever photographed, every spacecraft we've ever launched, every mile of interplanetary space we've ever crossed, all of it fits into a space so small that it barely registers against the interstellar gulf. The next time someone tells you that Proxima Centauri is the nearest star, remember what that word nearest is hiding. It's hiding a distance so vast that our entire solar system, the biggest thing we know, is swallowed whole by it. And we haven't even started trying to comprehend that distance yet. But we will. Because now that you understand how large the solar system truly is, now that you've seen the full scale of our cosmic home, you're finally ready to confront the true distance to Proxima Centauri. And I promise you, it's going to redefine everything you thought you knew about the word far. So now you understand the solar system. You've seen how vast it is. You've watched distances grow from the familiar to the incomprehensible as we moved outward from the sun, past the gas giants, past the ice giants, through the Kuiper Belt, and out to the immense spherical shell of the Oort Cloud, stretching nearly 2 light years from our star. You've seen how Voyager 1, after nearly 50 years of travel at 17 kilometers per second, has barely scratched the surface of that immensity. You have a sense now, at least intellectually, of how enormous the space is that we call home. Now it's time to talk about what lies beyond. It's time to meet Proxima Centauri, the nearest known star beyond our sun. And I want to be very clear about something before we go any further. When I say nearest, I need you to forget everything that word normally means to you. In everyday life, nearest means close. The nearest gas station is just down the road. The nearest hospital is a few minutes away. Nearest implies convenience, accessibility, a short trip. But in the context of stars, the word nearest is doing something very different. It's not telling you that Proxima Centauri is close, it's telling you that every other star in the entire galaxy is even farther away. Proxima Centauri is the least impossibly far. That's what nearest really means out here. It's not a measure of closeness. It's a measure of how much less unreachable something is compared to everything else. Let's start with what Proxima Centauri actually is, because before you can appreciate the distance, you need to understand the object we're trying to reach. Proxima Centauri is a star. It's a real physical ball of hydrogen and helium undergoing nuclear fusion in its core, converting matter into energy, producing light and heat just like our sun. But that's where the similarities to our sun mostly end. Proxima Centauri is a red dwarf. It's a tiny star by stellar standards. Its mass is only about 12% of the Sun's mass. Its diameter is roughly 215,000 kilometers, which is only about 15% the diameter of the Sun. If the Sun were the size of a front door, Proxima Centauri would be roughly the size of a softball. It's a small, cool, dim star that glows with a faint reddish light. How dim is it? Proxima Centauri's luminosity is only about 0.17% of the Sun's. Less than 2/1000ths of the light our Sun produces. Despite being the closest star to us beyond the Sun, you cannot see Proxima Centauri with your naked eye. That fact alone should tell you something about the distances involved. The nearest star to our solar system, the closest sun beyond our own, is so far away that even though it's a genuine star burning with nuclear fire, its light is too faint for the human eye to detect without a telescope. You can go outside on the clearest, darkest night, away from all city lights, with perfectly adapted night vision, and you will not see Proxima Centauri. It's there. It's real. It's burning. But it's too far away and too dim for your unaided eyes to pick up. Proxima Centauri is part of a triple star system called Alpha Centauri. The system contains 3 stars gravitationally bound to one another. The 2 main stars, Alpha Centauri A and Alpha Centauri B, are similar to our Sun. Alpha Centauri A is slightly larger and brighter than the Sun, a yellow star of roughly the same type. Alpha Centauri B is slightly smaller and cooler, an orange star. These two orbit each other every 79.9 years in a slow gravitational waltz that has been going on for billions of years. Proxima Centauri is the 3rd member of this system, but it orbits much farther out. It's roughly 13,000 astronomical units from the other 2 stars. That's about 2 trillion kilometers from Alpha Centauri A and B. Proxima Centauri takes roughly 550,000 years to complete one orbit around its companions. Its connection to the system is gravitational but loose, a tiny distant sibling circling the main pair from an enormous distance. And it's this tiny, dim, distant sibling that happens to be the closest star to our Sun. Red dwarfs like Proxima Centauri are the most common type of star in the Milky Way galaxy. They make up roughly 70% of all stars. But they're also faint that not a single red dwarf anywhere in the sky is visible to the naked eye. When you look up at the night sky and see stars, every single one of them is either larger and more luminous than our Sun, or it's not a star at all, but a planet reflecting sunlight. The most common stars in the universe are invisible to us without technology. We live in a galaxy dominated by dim red stars that we can't even see. There's something humbling about that. The galaxy's most abundant inhabitants are hidden from us by their own faintness. And yet, these tiny stars have a remarkable trait. Because they burn their fuel so slowly, they live for an extraordinarily long time. Proxima Centauri will continue to shine for trillions of years. Not billions, trillions. Long after our Sun has exhausted its hydrogen fuel, swelled into a red giant, shed its outer layers, and faded to a cooling white dwarf, Proxima Centauri will still be burning. In fact, no red dwarf anywhere in the universe has ever died of old age. The universe is only 13.8 billion years old. That's not nearly enough time for even the oldest red dwarfs to exhaust their fuel. Every red dwarf that has ever formed is still shining today. Every single one. Proxima Centauri is also what astronomers call a flare star. It periodically erupts with sudden, violent bursts of energy that can occur without warning. These flares can temporarily increase the star's brightness by a significant factor, releasing intense bursts of ultraviolet radiation and X-rays that blast outward into the surrounding space. For any planet orbiting close to Proxima Centauri, these flares would be devastating. They could strip away a planet's atmosphere, sterilize its surface, and destroy any complex molecules trying to form the building blocks of life. This is relevant because Proxima Centauri does have at least 2 known planets. One of them, Proxima Centauri b, orbits within the star's habitable zone, the region where liquid water could theoretically exist on a planet's surface. When this planet was discovered in 2016, it made headlines around the world. An Earth-sized planet in the habitable zone of the nearest star. The excitement was understandable, but the flares complicate the picture enormously. Even though the planet sits at the right distance for liquid water, the radiation environment may be far too harsh for life as we know it. But none of that changes the fundamental fact we're here to confront. The distance. How far away is Proxima Centauri? 4.24 light years. Let's unpack that number because it's the single most important measurement in this entire story. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. In 1 year, traveling at that speed every second of every minute of every hour of every day, light covers approximately 9.46 trillion kilometers. So 4.24 light years is 4.24 times 9.46 trillion. That comes out to roughly 40,140 billion kilometers. 40 trillion kilometers. 4 followed by 13 digits. A number so large that writing it out fills a line on a page. A number so vast that no analogy can truly capture it. Though we're going to try. Let's start with the most basic comparison. The distance from Earth to the Sun is 150 million kilometers. We established in the earlier part of this story that this distance is already enormous. It takes light over 8 minutes to cross it. Driving at highway speed would take nearly 2 centuries. Even the Apollo spacecraft would need over 5 months. That distance is already far beyond the reach of human intuition. And the distance to Proxima Centauri is approximately 266,000 times farther than that. 266,000 times the Earth-Sun distance. Take that already incomprehensible gulf of 150 million kilometers and multiply it by 266,000. That's how far away the nearest star is. Let me try to make that ratio tangible. If you shrank the Earth-Sun distance down to 1 inch, just 1 inch, the width of your thumb, then on that same scale, Proxima Centauri would be about 4.2 miles away. 1 inch to the Sun, 4 miles to the nearest star. Imagine standing in a room. The Sun is 1 inch from you. Every planet in the solar system fits within a few feet. Neptune would be about 30 inches away, roughly the length of your arm. The entire known planetary solar system fits within arm's reach. But the nearest star is 4 miles away. You would have to walk for over an hour to reach it. The contrast between those two distances, 1 inch and 4 miles, captures something essential about the gulf between our solar system and the nearest star. Here's another way to feel it. If the Sun were the size of a basketball sitting on your kitchen table, Earth would be a tiny grain about the size of a peppercorn sitting 26 meters away. That's already a significant spread for a scale model, but Proxima Centauri on this scale would be another ball, smaller than a marble, sitting roughly 6,900 kilometers away. 6,900 kilometers from your kitchen table. That's roughly the distance from London to Kolkata, or from New York to Tokyo by Great Circle. You could build your basketball sun and your peppercorn Earth in your kitchen in London, and the nearest star would be somewhere in eastern India. Everything in between would be empty. No planets, no asteroids, no comets, just void. A scale model of our solar system and its nearest neighbor would stretch across an entire continent and keep going, and almost all of that distance would be nothing. Emptiness. Silence. The cold vacuum of interstellar space. Let me try one more comparison. Imagine you're looking at a map of the United States. The entire map, from the Atlantic coast to the Pacific coast, represents the distance from the Sun to Proxima Centauri. On that map, the entire solar system from the Sun out to Neptune's orbit would be a tiny dot on the eastern coastline. Not a state, not a city, a dot. A point so small you might miss it if you weren't looking carefully. Everything humanity has ever explored in space, every planet we've ever visited with a spacecraft, every mile of interplanetary distance we've ever crossed, all of it would fit inside that tiny dot on the east coast. And the rest of the map. the vast majority of the distance from coast to coast, would be the interstellar void between our solar system and Proxima Centauri. The gap would contain nothing. No stars, no planets, no material of any significance, just the thin, cold interstellar medium, a sparse scattering of hydrogen atoms drifting through the darkness. Almost a perfect vacuum, stretching for trillions of kilometers in every direction. The emptiness between our solar system and Proxima Centauri is difficult to overstate. On Earth, we're used to things being between things. Between your house and the grocery store, there are roads, buildings, trees, people, cars. Between cities, there are farms, forests, rivers, mountains. Even the most remote deserts on Earth contain sand, air, wind, occasional life. Even the loneliest stretch of open ocean contains water, currents, marine life, dissolved minerals. There's always something between here and there on Earth. Always some medium, some substance, some evidence that the universe is filled with matter. But the space between the Sun and Proxima Centauri contains effectively nothing. It's not just empty in the way a desert is empty. It's not empty in the way the ocean depths are empty. It's empty in a way that nothing on Earth can prepare you for. The interstellar medium contains roughly 1 atom per cubic centimeter. One single hydrogen atom drifting alone in a cubic centimeter of space. For comparison, the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. The interstellar medium is so sparse that if you scooped up a volume the size of Earth from interstellar space, the total mass of all the atoms you collected would weigh only a few kilograms. The space between stars is as close to a perfect vacuum as nature allows. If you were somehow placed in the middle of that interstellar gulf, roughly 2 light years from the Sun and 2 light years from Proxima Centauri, you would see stars in every direction. Pinpoints of light scattered across the blackness, but none of them would be close. The Sun would be just another star in the sky, slightly brighter than most, but no longer the dominant blazing disk that rules Earth's daytime. It would no longer warm your skin or light your world. It would be a point, a cold, distant point of light that you could cover with a grain of sand held at arm's length. Proxima Centauri would be invisible to your eye because it's too dim. Alpha Centauri A and B would appear as a single bright star, among the brighter ones in the sky, but nothing extraordinary. You would be floating in a void so complete, so absolute, that the nearest solid object of any size would be trillions of kilometers away. The isolation would be total. The silence would be perfect. No sound, no warmth, no direction that leads anywhere in particular. And the darkness between the stars would stretch in every direction farther than you could travel in 1,000 lifetimes. This is the reality that the phrase nearest star conceals. It hides an ocean of emptiness 40 trillion kilometers wide. When you hear someone say Proxima Centauri is the closest star to the Sun, your brain naturally files it in the same category as other things that are close. But it's not close. It's inconceivably far. The only reason we call it close is that everything else is even farther. The next nearest star after the Alpha Centauri system is Barnard's star, about 6 light years away, already almost 50% farther than Proxima Centauri. After that, Wolf 359 at roughly 7.9 light years. Sirius, the brightest star in the night sky, is about 8.6 light years away. These distances keep growing, and they grow quickly. Within 10 light years of the Sun, there are only about a dozen known star systems. Within 20 light years, there are roughly 130. That's it. In a sphere 40 light years across, centered on our Sun, fewer than 150 star systems exist. The stars are spread out, separated by vast gulfs of nothingness, each one an island of light in an ocean of dark. Now, let's talk about why these distances are so hard for human beings to comprehend. Because it's not just that the numbers are big, it's that they're a specific kind of big that our brains were never designed to handle. Human beings evolved on the plains of Africa roughly 300,000 years ago. Our ancestors needed to understand distances that mattered for survival. How far is the watering hole? How far did the antelope herd move? How far is it back to the cave before nightfall? These distances ranged from a few meters to maybe 30 or 40 kilometers. That's the range our spatial intuition was calibrated for. We can estimate distances within this range with remarkable accuracy. You can look at a tree across a field and guess how far away it is within 10 or 20% without any tools. That's an evolutionary gift, honed over hundreds of thousands of years of natural selection. The individuals who were better at judging distances survived more often. They found food more efficiently. They avoided predators more effectively. They navigated home more reliably, and they passed those spatial skills to their descendants. But evolution only optimizes for what matters. And for our ancestors, nothing mattered beyond the horizon. There was no survival advantage to understanding the distance to the moon or the sun or the stars. Those things were just lights in the sky. Interesting to look at. Maybe useful for navigation or marking seasons, but their physical distance was irrelevant to staying alive. So our brains never developed the capacity to intuitively grasp large distances. We can learn to work with them intellectually. We can do the math. We can write down the numbers, but we can't feel them the way we feel the distance across a room. This is why large numbers all tend to feel the same to us. 1 million, 1 billion, 1 trillion. They all register as just big. Your brain doesn't automatically distinguish between them in the way it distinguishes between 1 meter and 10 meters, or between 10 meters and 100 meters. At those small scales, the difference is vivid and immediate. 1 meter is arm's length. 10 meters is across a room. 100 meters is down the street. Each step up by a factor of 10 changes how you physically relate to the distance. But when you jump from 1 million to 1 billion, a factor of 1,000, your brain doesn't flinch. It just files both numbers as really big. And when you jump from 1 billion to 1 trillion, another factor of 1,000, your brain still doesn't flinch. They're all just really big numbers. The differences between them don't register emotionally or intuitively, even though the actual differences are staggering. Let me illustrate this with time. 1 million seconds is about 11.5 days. That's comprehensible. You can imagine an 11-day stretch. You've lived through plenty of them. 1 billion seconds is about 31 years and 8 months. That's a significant chunk of a human life. It's the time between being born and entering your 30s. The jump from 1 million to 1 billion is the jump from 11 days to 32 years. Those feel completely different. And yet when someone says the words million and billion, they sound similar. They rhyme. They differ by only 1 syllable. The language disguises the enormous gap between them. 1 trillion seconds is about 31,688 years. That's longer than all of recorded human history. The jump from 1 billion to 1 trillion is the jump from 32 years to 32,000 years. From a single human lifetime to the entire span of civilization and far beyond. Now, apply this to distance. The distance to the moon is about 384,000 kilometers. The distance to the sun is about 150 million kilometers. The distance to Proxima Centauri is about 40 trillion kilometers. Your brain hears these as 3 big numbers. Big, bigger, biggest. But the actual ratios between them are mind-breaking. The sun is roughly 390 times farther than the moon. Proxima Centauri is roughly 266,000 times farther than the sun. That second jump is almost 700 times larger than the first jump. The gap between the sun and Proxima Centauri is proportionally far more enormous than the gap between the moon and the sun. And yet, when we list them, moon, sun, Proxima Centauri, they sound like a simple sequence. Step 1, step 2, step 3. The language makes it sound like a natural progression. It's not. It's a cliff, a vertical wall. Between the sun's distance and Proxima Centauri's distance, there's a chasm so vast that the entire solar system falls into it and disappears. This cognitive limitation is why astronomers developed the light year in the first place. They needed a unit of measurement large enough to make interstellar distances manageable. Using kilometers for the distance to stars would be like measuring the distance between countries in millimeters. Technically correct, but utterly impractical. The numbers become so long they stop being useful. They become strings of digits that no human can parse at a glance. But saying 4.24 light years is compact, memorable, and useful. You can compare it to other distances expressed in light years. If one star is 4 light years away and another is 40 light years away, you instantly know the second is 10 times farther. The unit provides a scale that the human mind can at least manipulate, even if the underlying distance remains beyond intuitive comprehension. But there's a danger in that convenience. Because 4.24 light years sounds small. It sounds manageable. It's a tiny little number with a decimal point. It fits neatly into a sentence. Your brain looks at it and thinks, that's not so bad. 4.24, less than 5. What's the big deal? The big deal is what's hiding behind those 4 innocent words. 9.46 trillion kilometers multiplied by 4.24. 40 trillion kilometers of empty space. A void so vast it dwarfs everything humanity has ever known, ever built, ever imagined. The tidy number is a mask. It's a label slapped onto something incomprehensibly large so that scientists can talk about it without their sentences running off the page. But don't let the label fool you. Behind those 4 words lies a distance that would take our fastest spacecraft tens of thousands of years to cross. A distance so large that light itself, the fastest thing the universe allows, needs over 4 years to traverse it. A distance that separates us from the nearest star by a gulf so immense that all of human civilization, all of human history, all of human achievement could be placed inside it and it would barely be noticed. And here's perhaps the most unsettling realization of all. This is the closest star. This is the nearest one. Every other star you've ever seen in the night sky, every star in every constellation, every point of light that has inspired myths and legends and navigation for thousands of years, every single one of them is farther away than Proxima Centauri. Many of them are much, much farther. Sirius is about twice as far. Vega is about 6 times as far. Betelgeuse is over 130 times as far. The stars you see at night are not nearby objects separated by modest gaps. They are nuclear furnaces burning at distances so enormous that even the nearest one is 40 trillion kilometers away. The night sky is beautiful, but it's also a profound deception. It looks intimate. It looks reachable. The stars seem to hang just overhead, scattered across the darkness like glitter on a ceiling. But that ceiling is an illusion. Those stars are separated from you by gulfs of emptiness so vast that crossing even the smallest of them would be the greatest achievement in the history of any civilization that accomplished it. That is the true scale of Proxima Centauri, not 4.24 light years, not a tidy number on a page, but 40 trillion kilometers of cold, dark, silent nothing between here and there. A distance that makes our entire solar system, everything we've ever explored, every world we've ever photographed, look like a single point lost in the void. A distance so extreme that it challenges whether the word distance even applies anymore. At some point, a gap becomes so large that it stops being a measurement and starts being a statement. A statement about the nature of the universe, about how space is structured, about how far apart things really are. And the statement that Proxima Centauri's distance makes is this: the universe is built on a scale that was never meant for us. The stars were never meant to be reached easily. The nearest one is already almost impossibly far away, and every other star in the sky is farther still. That's the reality hiding behind the phrase nearest star. And now that you understand it, now that you've felt the weight of those 40 trillion kilometers, there's one more question we need to answer. The question that matters most of all. What happens when you actually try to cross that distance? What happens when you take humanity's fastest machines and point them at the nearest star? The answer is going to show you just how far we are from being a truly interstellar species. So, the question on the table is this: could we ever actually get there? Could humanity, with all of its ingenuity and ambition and technological progress, ever cross the 40 trillion kilometers that separate us from Proxima Centauri? The answer depends entirely on what you mean by ever. And the different versions of that answer reveal just how profoundly the distance to the nearest star shapes our future as a species. Let's start with what we have right now. Today, the actual spacecraft humanity has built and launched into space. Not theoretical designs, not concepts on a whiteboard, real machines that have flown through the void and sent data back to Earth. Voyager 1 is currently the most distant human-made object. As we discussed earlier, it's been traveling since 1977 at about 17 kilometers per second. That's roughly 61,200 kilometers per hour. It's fast. Unimaginably fast by the standards of everyday life. At that speed, Voyager 1 covers roughly 1.5 million kilometers every single day without stopping. And yet, at that speed, Voyager 1 would need approximately 73,000 years to reach Proxima Centauri. 73,000 years. Let that number settle into your mind. Modern humans, Homo sapiens, have existed for roughly 300,000 years. All of recorded human history, every civilization, every empire, every invention from the wheel to the internet, fits within the last 5,000 years. Voyager 1 would need 14 times longer than all of recorded history to reach the nearest star. If Voyager 1 had launched when the last ice age was ending, when humans were still using stone tools and living in caves, when woolly mammoths still roamed the frozen plains of Europe and North America, when the Sahara was still a green savanna dotted with lakes, it would not have arrived at Proxima Centauri yet. It would still be traveling, still drifting through the interstellar dark, still surrounded by nothing but the faint glow of distant stars, and it would continue traveling for tens of thousands of years more before it finally arrived. Now let's try something faster. The Parker Solar Probe, launched in 2018, is the fastest spacecraft humans have ever built. It uses the sun's gravity to slingshot itself to extraordinary speeds. At its closest approach to the sun, the Parker Solar Probe reaches speeds of about 192 kilometers per second. That's roughly 691,200 kilometers per hour. About 11 times faster than Voyager 1. At this speed, you could travel from the Earth to the Moon in about 33 minutes. You could reach the Sun in about 9 days. This is genuinely fast. It's the fastest any human-made object has ever traveled. At the Parker Solar Probe's peak speed, the journey to Proxima Centauri would take approximately 6,800 years. That's a significant improvement over Voyager 1's 73,000 years. But 6,800 years is still an absurd amount of time by any human standard. That's longer than the entire history of civilization. The ancient Sumerians, generally considered the first true civilization, emerged roughly 5,000 years ago in Mesopotamia. They invented writing, built the first cities, developed mathematics, created legal codes, and laid the foundations for everything that followed. If you had launched a spacecraft at the Parker Solar Probe speed, when the Sumerians were scratching the first cuneiform symbols into wet clay tablets, that spacecraft would still be traveling today. It would still have nearly 2,000 years to go before reaching Proxima Centauri. Every empire that rose and fell in the ancient world, every war fought, every religion founded, every scientific revolution, every industrial transformation, all of human civilization from its very beginning to the present day, and still the spacecraft hasn't arrived. That's how far away the nearest star is, even at the fastest speed any human machine has ever achieved. And there's an important caveat here. The Parker Solar Probe only reaches its peak speed during close passes by the sun. It doesn't maintain that speed throughout its orbit. It speeds up as it falls toward the sun and slows down as it climbs back out. A spacecraft heading to Proxima Centauri couldn't use the sun's gravity to maintain high speed, because it would be flying away from the sun. It would need its own propulsion system capable of sustaining enormous velocities across trillions of kilometers. We don't have that technology. Nothing we've ever built comes close. So what about future technology? What about spacecraft that haven't been built yet but might be possible, based on physics we understand? This is where the conversation shifts from engineering reality to engineering aspiration, from what we've done to what we might someday do. And even in this more optimistic territory, the distances remain humbling. One of the most seriously discussed concepts for reaching another star is called breakthrough starshot. It was announced in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner. The idea is elegant in its simplicity, even if the engineering challenges are enormous. You build a spacecraft that weighs almost nothing. We're talking about a few grams, essentially a computer chip with a camera, a communication laser, and a navigation system, all mounted on an ultra-thin light sail made of reflective material, perhaps only a few hundred atoms thick. The whole thing would weigh roughly 1 gram, about the weight of a paperclip. Then you build a massive array of lasers on the ground, incredibly powerful lasers, with a combined output of about 100 gigawatts. That's roughly the total electricity output of 100 nuclear power plants, focused into a single beam of coherent light. You aim this laser array at the tiny spacecraft and fire. The laser light hits the sail and pushes it. Because the spacecraft weighs almost nothing, even the gentle pressure of light can accelerate it to tremendous speeds. The plan calls for accelerating the craft to roughly 20% of the speed of light. That's about 60,000 kilometers per second. 60,000 kilometers every single second. At that speed, you could travel from Earth to the Moon in about 6.4 seconds. You could reach the Sun in roughly 42 minutes. You could cross the entire solar system from the Sun to Neptune in about 21 hours. At 20% of light speed, a breakthrough starshot probe would reach Proxima Centauri in roughly 20 to 21 years. Add another 4.24 years for any data it collects to be transmitted back to Earth at the speed of light, and you're looking at about 24 to 25 years from launch to receiving the first information. That's within a human lifetime. You could launch the probe as a young adult and potentially see the results before retirement. For the first time in all the concepts we've discussed, we're talking about a timescale that a single human life could encompass. But before you get too excited, let's talk about the engineering challenges, because they are formidable. Some scientists would say they are currently insurmountable, and it's not clear they'll become surmountable within our lifetimes. First, the laser array. 100 gigawatts of focused laser power is beyond anything that exists today by orders of magnitude. The most powerful lasers in the world produce a few petawatts of power, but only for incredibly brief pulses lasting femtoseconds. Sustaining 100 gigawatts of continuous laser output long enough to accelerate a sail would require an energy infrastructure dedicated entirely to this single purpose. The laser array would need to be several kilometers across, consisting of thousands of individual lasers all working in perfect synchronization. Their beams combining into a single coherent pulse, aimed with extraordinary precision at a sail that's only a few meters wide. As the spacecraft accelerates and moves farther from Earth, the laser beam must track it with microscopic accuracy. Any drift and the sail moves out of the beam and acceleration stops. The tracking precision required is like shining a flashlight from New York and keeping the beam centered on a specific coin in Los Angeles while that coin is moving away from you at increasing speed. Second, the sail itself. It needs to be incredibly reflective, incredibly thin, and incredibly strong. It needs to reflect the laser light rather than absorbing it, because absorbing that much energy would vaporize the sail instantly. Current materials can't withstand the energy densities involved. New materials would need to be developed, perhaps based on metamaterials or exotic crystalline structures that don't exist yet. The sail also needs to be large enough to catch sufficient laser light to accelerate, yet light enough that it doesn't add significant mass to the spacecraft. The proposed size is about 4 meters across, but only a few hundred atoms thick. Manufacturing such a sail with current technology is not possible. Third, survival during the journey. At 20% of light speed, the spacecraft is moving at 60,000 kilometers per second. At that velocity, a collision with even a microscopic particle would be catastrophic. A grain of dust, 1/10 of a millimeter across, something you couldn't see with your naked eye, would hit the spacecraft with the energy of a small bomb. The interstellar medium, sparse as it is, contains enough gas atoms and dust particles that impacts are essentially guaranteed over a journey of 4.24 light years. The spacecraft would need some form of shielding, but any shielding adds mass, and mass is the enemy of the entire concept. The lighter the spacecraft, the faster the laser can push it. Add shielding and you need more laser power. More laser power means more cost, more infrastructure, more engineering challenges. The trade-offs are brutal. Fourth, communication. The probe needs to send data back to Earth from 4.24 light years away. The signal would travel at light speed, taking over 4 years to arrive. But the signal also spreads out as it travels. By the time it reaches Earth, the signal from a 1-gram spacecraft with a tiny transmitter would be unbelievably faint. Detecting it would require receivers far more sensitive than anything we currently have. The probe would likely need to carry a small laser to transmit its data back. But fitting a laser powerful enough to be detected across 4 light years into a 1-gram spacecraft is a challenge that borders on the impossible with today's technology. Fifth, navigation and data collection. The spacecraft would fly past the Proxima Centauri system at 20% of the speed of light. At that velocity, the entire flyby would last only a few hours at most. The probe would have a very brief window to photograph the star, its planets, and gather whatever scientific data it can before it flies past and continues into the void forever. There's no slowing down. Decelerating from 20% of light speed would require just as much energy as accelerating to it, and a 1-gram spacecraft can't carry that much fuel. It's a one-shot flyby. You get a few hours of data from a system that took 20 years to reach, and then the probe sails on into interstellar space, never to return, never to stop, drifting through the galaxy until the end of time. Despite all these challenges, Breakthrough Starshot is grounded in real physics. Nothing about it violates any known law of nature. The speed of light isn't being exceeded. The physics of light pressure is well understood. The concept is feasible in principle, even if the engineering is far beyond our current capabilities. Some optimistic estimates suggest that with dedicated funding and research, a prototype could be launched within a few decades. More conservative estimates place it further out, perhaps a century or more. And some scientists quietly suspect that the engineering challenges may simply be too great. That the concept works on paper, but may never work in practice. Even if Breakthrough Starshot succeeds, it's important to understand what it would and wouldn't achieve. It would send a tiny probe past the nearest star. It would give us a few hours of close-up data from Proxima Centauri. That would be extraordinary. A milestone in human exploration that would rank alongside the moon landings and the first images from Voyager. But it wouldn't be interstellar travel in any meaningful human sense. It wouldn't carry people. It wouldn't establish a presence at another star. It wouldn't allow us to visit Proxima Centauri's planets or study them up close for more than a few fleeting hours. It would be a flyby, a brief glimpse, a postcard from the nearest star. Precious and historic, yes, but not a bridge, not a road, not a connection between here and there. What about sending humans? What would it take to send actual people to Proxima Centauri? The honest answer is that we have no idea how to do it and no plausible path to learning how within any foreseeable time frame. The challenges multiply beyond comprehension when you replace a 1-gram chip with a crewed spacecraft. A crewed interstellar mission would need to carry people, food, water, air, medical supplies, spare parts, fuel, radiation shielding, and everything else needed to sustain human life for decades at a minimum. The spacecraft would weigh thousands or millions of tons. Accelerating that mass to even a modest fraction of light speed would require energy on a scale that dwarfs anything humanity has ever produced. And you would need to decelerate at the other end, which doubles the energy requirement. You'd also need to keep the crew alive and healthy for the entire journey, protecting them from cosmic radiation, providing artificial gravity to prevent bone and muscle deterioration, maintaining their mental health during years or decades of confinement in a small vessel surrounded by nothing. If you couldn't reach a significant fraction of light speed, the journey would stretch into centuries or millennia. This leads to the concept of generation ships. Vast spacecraft designed to support entire communities for hundreds or thousands of years. The people who launched would not be the people who arrived. Their distant descendants, perhaps hundreds of generations removed, would finally reach Proxima Centauri. These descendants would have been born on the ship, lived their entire lives on the ship, and would arrive at a destination they knew only from stories and records passed down through centuries of oral and written tradition. The ship would be their entire world, a moving civilization carrying the legacy of Earth across the interstellar void. They would know no other sky than the walls of the vessel that contained them. They would have no memory of grass or rain or open horizons. Only the hum of machinery and the knowledge that somewhere ahead, a star was waiting. But the practical challenges of maintaining a closed ecosystem, a stable society, and a functioning spacecraft for thousands of years are so immense that most scientists consider generation ships to be firmly in the realm of science fiction. We can barely keep a space station functioning for a few decades. Maintaining a self-sustaining habitat for millennia is a challenge of a completely different magnitude. So where does this leave us? It leaves us with a profound and uncomfortable truth. The nearest star, the closest sun beyond our own, is so far away that reaching it represents perhaps the greatest challenge our species will ever face. It's not a matter of building a better rocket or inventing a faster engine. It's a fundamental confrontation with the scale of the universe itself. The distance to Proxima Centauri isn't a problem to be solved with engineering. It's a feature of reality. It's how the universe is built. The stars were placed by the blind mechanics of gravity and gas dynamics at distances that make travel between them a civilizational undertaking of the highest order. And remember, Proxima Centauri is the nearest one. Everything else is farther. Barnard's star is 6 light-years away. Sirius is 8.6. The center of the Milky Way is 26,000 light-years away. The nearest large galaxy, Andromeda, is 2.5 million light-years away. If reaching the nearest star would take 20 years at 20% of light speed, reaching the center of our galaxy at the same speed would take 130,000 years. Reaching Andromeda would take 12.5 million years. The galaxy, let alone the universe, is structured on a scale that makes interstellar travel not just difficult, but potentially forever impractical for biological beings like us. This doesn't mean we should stop trying. The history of human achievement is a history of doing things that seemed impossible. No one thought heavier than air flight was possible until the Wright brothers proved it in 1903. No one thought humans could survive in space until Yuri Gagarin orbited Earth in 1961. No one thought we could walk on the moon until Neil Armstrong did it in 1969. Each of these achievements pushed the boundaries of what was considered possible, but each of them also operated within the laws of physics. Planes fly because aerodynamics allows it. Rockets reach space because Newton's third law allows it. The speed of light, however, is not a technical limitation we might overcome with cleverer engineering. It's a fundamental law woven into the fabric of space-time itself. We can approach the speed of light, in theory, with enough energy, but we can never exceed it. And even approaching it requires energies so vast that they strain the imagination. What does all this mean for how we see ourselves? What does the distance to Proxima Centauri tell us about our place in the universe? It tells us that we are isolated, not metaphorically, physically. The nearest star is separated from us by a gulf so wide that crossing it would take our fastest existing spacecraft 73,000 years. Even the most ambitious future concepts propose journey times measured in decades. We are surrounded by stars, yes. On a clear night, you can see thousands of them. They seem close, familiar, almost friendly, but every single one of them is separated from us by trillions of kilometers of empty space. We live on an island, and the nearest island is almost impossibly far away. It tells us that the night sky is a profound illusion. When you look up and see the stars scattered across the darkness, your brain interprets them as nearby objects. They look like they're just up there, hanging above you, close enough to touch if you could only reach high enough. But they're not up there. They're out there. Way out there. Each one separated from us and from each other by distances so vast that light itself needs years to cross them. The beautiful, intimate canopy of stars is actually a collection of nuclear furnaces burning at distances that would take thousands of human lifetimes to traverse. The night sky isn't a ceiling. It's a window into an abyss. It tells us that Earth is precious. Whatever you think about the possibility of life elsewhere in the universe, the fact remains that getting to any other potentially habitable world is extraordinarily difficult. Proxima Centauri b, the planet orbiting in Proxima Centauri's habitable zone, might have the right conditions for liquid water. Or it might be a radiation-blasted wasteland scoured by stellar flares. We don't know. But we do know that reaching it is beyond our current capability, and may remain so for centuries or longer. Earth isn't just our home. For all practical purposes, for this generation and many generations to come, it's our only home. The only world we can live on. The only world we can reach. The only world where we know for certain that the conditions are right for human life. Every other potentially habitable world is locked away behind trillions of kilometers of void, sealed off by distances that mock our fastest machines. This should make us think very carefully about how we treat the one planet we have. But it also tells us something beautiful. We figured this out. We measured this distance. We calculated the travel times. We designed concepts for spacecraft that could theoretically make the journey. We understood the physics well enough to know what's possible and what isn't. We are small creatures on a small planet, orbiting an ordinary star. And yet we comprehended the scale of the universe that surrounds us. That's extraordinary. No other species on Earth has ever done this. No other species has ever looked up at the stars and understood what they were seeing. We are the universe becoming aware of itself, at least in this tiny corner of space. And that awareness, that capacity for understanding, is worth something. It might be worth everything. The distance to Proxima Centauri is 4.24 light years, 40,140,000,000,000 kilometers, 266,000 times the distance from Earth to the Sun. A gulf so vast that our fastest spacecraft would need 73,000 years to cross it. A distance that makes our entire solar system look like a single point of light, lost in the darkness. That distance is real. It's not going away. It will be there tomorrow, and the next day, and the next century, and the next millennium. The stars are far away, unimaginably, stubbornly, almost cruelly far away. And no amount of wishing or hoping or dreaming will change that. The universe is not built for easy travel between stars. It's built on a scale that dwarfs everything we are and everything we've ever done. But we know this now. We understand it. And understanding the true scale of Proxima Centauri, understanding what those 4.24 light years really mean, is itself a kind of journey. Not a physical one, but an intellectual and emotional one. A journey from the comfortable assumption that the stars are within reach to the humbling realization that even the nearest one sits behind a barrier of distance, almost too large to comprehend. And perhaps that's enough. Perhaps knowing where we stand, knowing how vast the darkness is between here and there, knowing how small we are and how large the universe is. Perhaps that knowledge is its own reward. It connects us to reality. It grounds us. It reminds us that we are part of something enormous and ancient and ongoing. The universe doesn't owe us easy access to the stars. It doesn't owe us proximity or convenience. It simply is what it is. Vast, cold, beautiful, indifferent. And we are here, on one small world, looking out at all of it with the only eyes that, as far as we know, have ever looked back. So the next time you step outside on a clear night and look up at the stars, remember what you've learned. Those points of light are not decorations on a dome. They are distant suns, each one separated from you by distances measured in trillions of kilometers. The nearest one, Proxima Centauri, sits 4.24 light years away. Too dim to see with your naked eye, too far to reach with any technology we possess. And every other star you can see is farther still. The universe is vast. The stars are far. And you, standing on the surface of one small planet, looking up at all that immensity with nothing but your own eyes and your own curiosity, are part of something so large it defies comprehension. But you're also something the universe has never produced before in this corner of space. A mind that can look out at 4.24 light years of empty darkness and understand what it means. That understanding is rare. It might be unique in this part of the galaxy, and it connects you to those distant suns across all those trillions of kilometers, not physically, but through knowledge, through awareness, through the simple, profound act of looking up and knowing what you're seeing. The stars are far away, but tonight you understand just how far. And that understanding, that hard-won knowledge about the true scale of Proxima Centauri, is a kind of bridge across the void. Not one you can walk across, but one that connects you to the cosmos in a way that nothing else can. Thank you for taking this journey with me tonight. If you found this exploration meaningful, a like or subscribe would mean a great deal. It helps me continue making these deep explorations of the universe and our place within it. Sleep well tonight under the stars. They are farther away than you ever imagined, but they are also yours. Every photon that crosses the void to reach your eye is a message from a distant sun. A tiny packet of energy that has traveled for years through the darkness just to land on your retina in this single moment. A reminder that the universe is vast and beautiful and real. And you are here to see it. That matters more than distance ever could. Good night.